Hey time traveler, we're gonna do one of the classic physics problems called angle of repose, and I'm just gonna talk about friction for a little bit. So the formula for friction is friction is equal to mu naught, so that's the coefficient of friction, times the magnitude of the normal force. And there's a couple of components to this. If I have something sitting flat on the ground, it's going to equal up to this. And it is sitting on the ground with nothing acting upon it. The FBD, you guys are going to find out, I'd love myself a good FBD, is going to look like this, where the normal force and the gravitational liquid weight force are directly canceling. Pretend those arrows are neater. And you can say that this object is therefore at rest because the net force is equal to 0. So force equals mass times acceleration. If force is equal to 0, if net force is equal to 0, then the acceleration is equal to 0. If I am pushing on it a little bit, so I'm adding an applied force, then I will have a friction force. I have been taught to use a curly F. Some people do an F with an F subscript. It's actually really across the board. I haven't really seen any sort of consensus on it. Everyone seems to just hate everyone else's conventions. This is the convention I use. I use curly F. So if you see me use curly F, I mean friction. And we're going to use these to show that it's in equilibrium. And we are going to say this is static friction. There's two types of friction. There's static friction, where it hasn't started to move yet, and kinetic friction. And what we know is that static friction is always a little bit higher than kinetic friction. This obviously makes sense because if I start moving something and it experiences more kinetic friction than it did static friction, then it's going to slow back down and we're going to be in static friction. It's also easier to just move something where the surfaces are already sliding against each other than it is to start those surfaces to slide. But that's the gist of it. Those are my 2 cents on friction. One thing to note is that it's the absolute value of the normal force. So say we're on an incline like this, even though my normal force is in this direction, my static force is going to be in this direction, opposing the movement of it trying to slide down. And that's always going to be the case. Friction is what you add last, because friction will always oppose whatever movement is trying to be made. Friction will always go against the direction of velocity, I guess. So it doesn't necessarily have to be added last, but if your object is at rest, add it last, because you know it's going to need to cancel out everything. Obviously, friction is not magical, but those are my 2 cents. Yeah, so friction is a force that opposes motion. One thing that I think is really helpful after you get past kinematic equations is to start describing every term in your own words. If you can describe what friction is in your own words, it's a force that opposes motion. That is as descriptive as I need it to be. Does it capture every single nuance? No, but it's a good understanding of what friction is. And that's what I'll say for any and all sort of forces and stuff going forward, is trying to have your own sort of definition. And if you're thinking about studying for the exam, one of the best things that you can do, and something that I've been recommending, is make your own equation sheet. And that is to say, when I write this out, what do I mean by all of this? I mean, this is a force that opposes motion, so that's going to be this directional hat. It has a coefficient of friction, which is this, and it can be up to this coefficient of friction times the normal force. But after that, it turns into kinetic static friction, or kinetic friction, not kinetic static friction, which is the same equation but with a different coefficient of friction. Okay, that was a lot. Let's start on the angle of repose stuff. So, how do people calculate the static friction of something? They do it with something called the angle of repose. So let's say we have something with non-negligible friction. We're going to say a wood, mass of G, a mass of M, and this is going to be at an angle of theta. You'll notice for a lot of mine, I don't really care about adding numbers to mine. I just feel like it's not super necessary. We can add numbers at the end if we want. And we want to find out at what angle does this block start to slide. So we can start out by drawing, you guessed it, an FBD. You should get really used to drawing these FBDs. So we can say at max, friction force is equal to this times the magnitude of the normal force. Sorry, I know my W's and my N's look really similar. It's always been a problem, especially in physics when they're usually quite good friends. So we're going to say it's when this is equal to this and when that is equal to the cosine component of this. And we say that because, sorry, there's a motorcycle outside? Hello? Anyways, we're going to say the x component here and the x component here have to equal out to each other, because once this wins, it's going to start sliding down the ramp. And we're going to assume that the y components, like, it's not falling through the floor, it's not going to God, it's chilling. So we're not worried about that. All is to say, your friction force is equal to this at max value, and that's going to be equal to your cosine times your weight force. So let's fill this out. We know that the magnitude of the normal force is is that right? I feel like I am so sorry, guys. I have my sine and my cosine flipped. So we're just gonna scribble that out. And if you have that on an exam, I think that is perfectly fine to just be like, add and it's honestly fine. Like, physics is really nice like that. Like, if you make a mistake, you just sort of correct it. So now we can just say, wait. We can say, and tangent goes between -1 and 1. Oh, totally lied. I forgot how tangent works. It can be greater than 1, although uncommon. Tangent goes to infinity, because you can have a rise of very large for a very small run. So that is the angle of repose, and we can take the arctangent of the coefficient of static friction to... Okay, so before my phone died, I was just saying, you can use your angle to find your coefficient of static friction, or you can use your coefficient of static friction, or you can find your coefficient of static friction using your angle. And so Oh, one thing that's interesting is scientists will sit in their laboratories all day testing different surfaces and different like objects, and they will literally just find the angle at which the object slides, and there's a huge database. It's like wood against cloth, cloth against oil, like paper against plastic, plastic against, it's this huge repository of information, and that's how they understand, like this is how they understand friction and how friction interacts between different objects. So I just think it's kind of interesting that with physics that you can learn in like 2 weeks, that's something that people spend their whole lives dedicating to, is like the study of friction, which is actually what Brian did. Yeah, so hopefully that makes sense. It's a fun classic physics problem. All right, good luck, time traveler. You got this. I believe in you.